Phosphorus tribromide is a dense, colorless, and sometimes scary liquid. It doesn't have many immediately remarkable properties, but it does fume profusely when exposed to moist air. It's pretty reactive with water, so when it touches the moist air, it quickly reacts with it and forms hydrobromic acid. To be totally honest, I made the phosphorus tribromide because I thought it would be fun, and its use was actually more secondary. However, to justify making it, I did end up using it in the way that it's most commonly used, and this is for the bromination of alcohols. In very simple terms, an alcohol is pretty much just an organic molecule which contains an OH group. If the OH group is swapped for something like a bromine, it actually opens up the molecule to a lot more reactions. I used my phosphorus tribromide to make bromopentane, and in the future I'll use it to make something called 1-octen-3-ol. Unfortunately, this chemical doesn't have a better common name, but it's interesting because it's actually the chemical that attracts biting insects like mosquitoes. Okay, so enough of the chit chat and let's get started on the synthesis. Starting with a 100 milliliter flask, I pour in about 20 milliliters of bromine that I made in a previous video. Above, I've attached a condenser, and on the side you can see I've weighed out about 10 grams of red phosphorus. I started stirring the bromine using my magnetic stirrer, and I attached the water recirculator, but I don't turn it on. I attached it just in case the bromine starts boiling violently or it gets out of control, and I have some method of keeping the vapors down. In the end though, I found that this was completely unnecessary and no recirculator is needed at all. So to start, we take some of the red phosphorus on a spatula and we pour it in. You can actually see that the moment it touches the bromine, it lights on fire. The fire occurs because the reaction between the bromine and the red phosphorus is so exothermic that it ignites the red phosphorus. This is expected for the first addition, but after this, there won't really be any oxygen left inside the flask, so there should be no fire. The long tube above the flask helps to limit splashing, and it also keeps oxygen out. This makes the addition just a little bit safer. The first half of the red phosphorus has to be added pretty slowly because the reaction is pretty violent. You can see that by just putting a little bit in, a large puff of smoke comes out. What's occurring here is really two different reactions. The first reaction is the very exothermic one between phosphorus and bromine to form phosphorus tribromide. If an excess of bromine is present, it can react with the phosphorus tribromide to form phosphorus pentabromide, but this reaction is reversible. With a little bit of heat, we can break down the phosphorus pentabromide back into phosphorus tribromide and bromine. If we make sure that there's an excess of phosphorus present, it will sequester the bromine and prevent it from going back to the phosphorus pentabromide. So during the beginning and for most of the addition, there will be an excess of bromine and we will be forming quite a bit of PBr5. However, at the end, we'll have an excess of phosphorus and we'll heat the reaction to push it back towards the PBr3. If the reaction is cooled, it will help keep it under control, but it's not absolutely necessary. You can see that some flaming phosphorus just fell as I was adding it, so for this reason, it's obviously a good idea not to have any flammables around. At the top of the condenser, I scrape off what appears to be white phosphorus that is formed. And the moment I take it out of the condenser and it hits air, it lights on fire. You can see near the end of the addition that I can add quite a lot of red phosphorus and not much happens. To finish off the red phosphorus, I pour the rest of the phosphorus from the beaker and a little bit of fire starts. This is a really dirty process, but just to clean things up a little at the end, I try to scrape some of the red phosphorus from the sides and knock it down. So after the addition, in the reaction flask, we're left with a mix of yellow, red, and black. The next thing we do is we bring the mixture to a reflux. As we reflux the small amount of PBr3 that we have, we can see that the PBr5 is breaking apart back into bromine, but the red color of bromine isn't disappearing. This indicates that the phosphorus is not in excess and we'll need to add more. Although 10 grams was calculated to be in excess, The reason why mine isn't is probably because my phosphorus is pretty old and not great quality. On top of this, a little bit of it burned when trying to add it, and a lot of it got stuck inside the condenser. To remedy this, it's pretty simple, and we just pour another scoop or two down the condenser. Before the phosphorus is added, it's important to stop refluxing it just for safety reasons. Immediately upon adding it, even without a reflux, the flask cleared up. Now, as we heat it up again, we can see something pretty interesting. You can see the yellow PBr5 breaking back down into PBr3 and bromine. However, this time with an excess of phosphorus, the bromine is quickly taken up and the red color doesn't persist. As we heat it, eventually the front will make it to the condenser column. At this point, the recirculator is attached, but we don't run water through it because it's really not needed. I thought it was very satisfying to watch the front of the PBr3 move up and kind of clean my glassware. Because of the red color of the bromine, it really looked like my glassware was bleeding. So we keep refluxing it until everything more or less clears up. In the reaction flask, we're left with a suspension of black junk in PBr3. To clean the PBr3, we decant it into a 50 milliliter round bottom flask with some red phosphorus at the bottom. The red phosphorus at the bottom serves as pseudo boiling stones, and it also keeps the equilibrium in favor of PBr3 over PBr5. So we quickly set it up for a simple distillation. Because the boiling temperature of PBr3 is so high, we don't need to run water through the condenser. It's more than sufficient just to have it air-cooled. So we crank up the temperature and we bring it to a boil. It had a little bit of trouble making it over, so I insulated it with a little bit of aluminum foil. Very shortly after, we'll start to collect some of our PBr3. The fraction I collected was between 168 and 172 degrees Celsius, and when it started to rise above that, I stopped it. What we got was about 17 milliliters of slightly cloudy PBr3. This actually corresponds to the exact same yield as the guide that I followed. Normally, if you want to store it, it should be ampuled like I did to my bromine, but because I plan to use it right away, I simply just stoppered the round bottom flask that it was in. You can see in the distillation flask that there's not much left over except for some excess phosphorus. Just as a side note, my PBr3 came into contact with a minute quantity of sulfuric acid. It immediately turned a yellow color, and even after distilling it again, it maintained this yellow color. If any of you guys maybe have an explanation for this, I'd love to hear it. So now to play with the PBr3, but it's important to be careful because it's quite dangerous and you can see the fuming that comes off it. The fumes are of hydrobromic acid when the PBr3 reacts with water in the air. Anyway, to start messing around with it, I first put a little bit into a test tube. And then on top, I pour in some water and nothing happens. I even pipette some more in and it just sinks to the bottom. It's pretty interesting that a lot of these liquids that are pretty reactive with water, when mixed, they kind of just separate and not much happens. I assume this is because since they're totally immiscible and one sinks to the bottom, the surface area between them isn't enough to really get a vigorous reaction going. When PBr3 reacts with water, it should form phosphorus acid and hydrobromic acid. You can see here that when I shake it and I increase the surface area between the two, the reaction's much more vigorous and all the PBr3 quickly reacts. Above we get a nice white dense cloud of water vapor and hydrobromic acid. Then for the finale, I pour the rest into water. You can actually see here where the orange contamination came from. I tried to be cool and lubricate my stopper using concentrated sulfuric acid, but apparently the PBr3 didn't like that. So that's the reason for that, and I guess the lesson is to not do that. So we can see here with this larger quantity that the reaction gets going much faster and the water will start to boil around it. I'm sure if I shook it around it would be much more vigorous, but it was going pretty well on its own. As the reaction picked up, it released more and more hydrobromic acid vapor. For obvious reasons, this should be done in a well ventilated area, otherwise, you're going to fill the room you're in with hydrobromic acid vapor. Even though my garage is pretty well ventilated, you can see here that the vapor is everywhere. Again, here's a list of the videos that I'm currently editing and future videos I plan to film. In the videos being edited category, you can vote for the one that you want me to publish next, and in the future video category, you can vote for the one that you want me to film next. Also, if you're feeling generous, please donate to my Patreon account because with a bigger budget per video, I can do more things. Anyway, that's all for now, and I'll see you on the next one.